what I'll do here is moderate a discussion panel with these wonderful experts that give some talks today. And the goal of this is to brainstorm on broadly what we have been discussing, which is the use of coherence. What are we going to do with it? What are the, even grander things that we've heard of? What can we think about? So Sophie did something very clever, which is she started to ask for questions, and some people already posed some questions, it turns out. Is there anything deliverable that we should come up with?
Is there anything deliverable?
Deliverable, like a report or something?
We will be.
We're going to take some notes, right?
Yeah, we're gonna take some notes, and maybe you should put up, Sophie, can you put up those three things that the workshop is supposed to get out, like community and things like that, because those are larger goals that we have set ourselves.
Okay, so the goals are, well, the goals of the workshop are listed up there. Educate users on what coherence can do. I think we did a fantastic job on that. Foster a community around the topic, and I think there's some ideas that we can explore in this conversation. Third one that I cannot see. Identify potential optical or instrumentation developments. You can see it on this corner here. So that's the goal of here is to start the discussion and see if some of these can be further developed or discussed. So again, there were some questions that were put on some system to take questions, and I'm reading those questions and seeing those questions here. I'm going to start off with some questions posted there that were upvoted. In case you don't know what that is, basically some of you voted on questions that you really want to hear the answers to. The most popular question is the following. What emerging trends or innovations in X-ray coherent techniques do you believe will have the most significant impact on advancing material science research in the next 5 years? Bit of a mouthful, but what emerging trends or innovations, X-rays or electron microscopy, we'll just throw it in there, will have the most impact? Well, what are the biggest, trends that will change material science as we see it?
An X-ray person should start.
I believe that it's probably what is missing is the full 3D reconstruction, but in a native way. You have ptychographic reconstruction and you have slicing, but it's not still, if I understood it correctly, it's not still complete. More or less some of the problems that were also brought on by electron microscopy. So being able to make a full reconstruction, or even, I don't know, maybe in the sense that you were trying to say, right? With going beyond the kinematic approximation with the dynamic approximation. So really trying to keep into account the fact that we are traveling through a sample, and then there is an interaction volume, and then it comes out, and this can be, yes, moved around, but it has to figure out that there is a before and after somehow, right? And making everything consistent, that would be, I guess, transformational, because it would go closer to what others do in other ways, but with the characteristics and the capabilities of X-rays. Maybe even being resonant, and so being looking at the part that are not the principle you are scattering out of, but the other that are the principle we are interested in. But this is certainly something that I would.
Yeah, it's been what you're talking about is widely deployed in optical imaging and in electron imaging. So there's no reason it couldn't be brought to coherent X-ray imaging too. And you can do things we can't, like spectroscopic resonant, pre, on, and post edge to get things like chemistry. We will never be able to do that. So I think computational power is there. The algorithms are published. It just needs a good enough, coherent enough beam and a huge GPU memory pool.
The other thing, I'm thinking about all the time is because, this optical community, it's easy to get, access to this coherence sources, much easier. So a lot of tweaks or tricks they play with the coherence, right? Like you say, this or what's that, orbital angular momentum thing, right? Without coherence, it's very hard to achieve. But now with, I mean, it's not still fully not coherent, but in LS, which is much better than EPS, but we still have 10% of coherence, which is considered almost full, not full for hard X, almost full coherence. But what I'm saying is there are a lot of tricks that in the optical community, we should be able to think about from X-ray point of view. We can borrow all the techniques, even the method to X-ray, communities. We can try all different, like Laurie mirror I mentioned, right? X-ray is impossible, but now with high coherence, we can do it now.
In terms of, we steal most of our ideas from the optical or astronomy.
Yeah.
In terms of imaging, to me, the fighting for resolution is always showing some conflicting with field of view. So if you put other way, if you want to achieve high resolution, you have to limit your field of view, and that could be potentially a problem, because if you only image a small area or image a few particles, we need to, at least for me, with our beamline, we keep asking the same question whether the area we measure is representative or not. So a recent development or breakthrough in high resolution X-ray imaging is they adapt this laminography geometry, and they can realize like continuous zoom in and out capability in X-ray imaging in 3D. So I think the idea is like you survey a relatively large area with relatively lower resolution, and then one gets statistical information, two is to locate the region of interest, and then you can zoom in to high resolution. I think that could be a good approach for a lot of questions that requires statistical information.
I want to add one more thing. So the other thing that I think everybody is talking about is multimodal detection, right? With the coherent imaging, XPCS, everything, but the technique itself won't solve all the problem. Like you mentioned, we have a bubble in there, the dynamic scattering there. How do you do it? I'm not saying this coherent imaging can solve everything, but if we have multimodal, like you combine with, I don't know, fluorescence maybe, right? Spectroscopy, even put some AFM or microscope on it, that will help to eliminate a lot of uncertainties during the characterization.
Yeah, correlative and multimodal.
Yeah.
And you can even do sensor fusion. You can actually directly put the channels together if they're measured at the same time. And it, as you say, it's so powerful because you have totally orthogonal measurements that can be combined. The mathematical framework is published, it exists, right? Just need the data.
Yeah.
Right, excellent. So can did everybody catch that, or comments from the audience about that? I think the first one that I think would give us would be something to the effect of 3D type imaging, right? With depth and kinds of resolutions. Is that a fair summary of what you kind of raised? Just to have something like quasi concrete and larger or adaptable field of view to some extent. And then multimodal. That's the other one. Okay.
See, this is what I was trying to address with I said there are keywords that I use, but one of which was multimodal. But there is a difference between being extrinsic. So you have, for example, you have one sample that you bring, let's say from beamline to beamline, from experiment to experiment, right? And you try to integrate at the level of the data, everything, but you need registration marks. There are challenges, obviously. You try to do it intrinsically, as Xiaojing was presenting, right? At the same moment where you collect one signal, you collect also another one, or maybe in different moments if you want, but still in the same setup somehow, right? So the level of control obviously is higher, and this allows you better integration. And then there is the entangled way of doing it somehow, or mixing the mixing, call it as you want. In the sense that really you are extracting some orthogonal information, as was told before, and at the same moment, but really under the same level of control somehow that you have. And if we can integrate everything, indeed, that would be a game changer as well, of course.
Okay, so the questions again were ranked as in terms of upvotes, but I'd like to go to a question that is more or less limited, and we'll go back to the one that is next on the ranking. The one that is next on the ranking, which is related to what I just asked, is what are the limitations hindering us from getting to these goals? And how can they be overcome?
One of them is certainly was clearly shown, right? I mean, there is computational power, there is storage of data or quantity of data, there is time and energies to retrieve everything. But even from the experimental point of view, having enough photons, right? Because still we are coherent, as we said, but up to a certain level with limitations and whatever. But even managing the sample, I mean, I'm surprised that we can actually do what was proposed, what was shown already, right? Turning around a sample with the precision of the size of the beam, which is micron or few microns, is non-trivial, especially because we are in reality, you're starting to make everything to rotate that is sizable, is large, is heavy, right? And still you can keep a control that is surprising. Obviously, with electrons, sometimes you have advantages and they exploit it exceptionally well. It's tough. It's tough. It's really tough. And if you plug in this as an uncertainty together with everything else that you have to discover, fit, modelize, whatever, obviously it's an explosive matter that you're trying to handle, right? Somehow. So this is a tough. It's still a tough task. I would love to make ptychography and tomography on our end station. Our sphere of confusion is not really adapted to do it. That's it. It's as simple as this, at least not for the moment. Maybe you will tell me, suggest beautiful mathematical instruments to try to keep everything.
Yeah, maybe I will follow up on that. Yeah, the data problem in 2D is currently tractable. In 3D, it is so difficult, especially if you do multi-scale or multimodal, right? There's just so much information recorded that you have to register on so many scales. And our stages are pretty stable, right? But not stable enough. Those tomographic reconstructions I showed you guys, every single one of them is months to align the data. It's still, every new sample has a new algorithm, new method. Many thousands of graduate student tiers have gone into each of those reconstructions. In 2D, it's a solved problem, I think, more or less, mostly automated, I'd even say. 3D, oh my goodness, we're not ready, right? Because you do step sectioning, you might increase the dimensionality of your data by factor 10, factor 20. But once you go to true three-dimensional voxels, your field of view could easily be 100,000 by 100,000 by 100,000. And we are so not ready for that. And I did want to say electrons are amazing, but if you put everything we've ever looked at together into a cube, it would be about a centimeter cubed, right? And I mean my facility for 35 years. So our field of view is we're getting up to micron scale now. We're very proud of our 1 micron by 1 micron field of view.
I can think about two limitations right now. One is the radiation damage. Like we always trying to improve the storage ring, increase the coherence flux density. But in the meantime, we keep asked by the same question from the community: what's the whether your sample ready to handle those photons before you measure what you want to measure? And there are tons of simulation showing that, right? So maybe no matter what you do, maybe there's a physical limitation and you cannot just go beyond that limit because the sample is going to be destroyed. So to me, generally speaking, maybe you can have two categories of approaches to tackle this problem. The first one is I would say is a passive way, like cryogenic cooling to slow down this process. Another way maybe is more promising, maybe is active ways like to do some sparse sampling, trying to get same information and remove the unnecessary exposures. Those eventually the radiation damage is going to be the limiting factor to how far we can go. Another side, you guys touch base the data analysis. You just mentioned the 2D problem is solvable, yes or no. So let's say we have we're building brighter and brighter light source, and we can run to the measurement faster and faster. So let's say for typography reconstruction, right now we heavily use this iterative reconstruction engine. because it's iterative, it takes time. And now we're already hitting the point that the measurement itself is much faster than the 2D reconstruction. So you can imagine if we keep doing this, once the experiment is done, it still takes days, weeks to finish the data analysis. And in the meantime, maybe the users, ideally, they want to see the preliminary result to decide what's going to do next, right? So this at least for our being now, we're hitting this bottleneck, like the measurement can be done faster than the data analysis, even for the basic 2D reconstruction, if we keep using this iterative reconstruction engine. So I think now there's some development to use the machine learning technique to train the model, and then for some cases they can give the instantaneous reconstruction, grab the data, and then give you a result immediately. How reliable it is, I think given time, it's going to be work better and better. And to me, that probably that have a much better chance to catch up with the measurement.
So the sparse approach you are trying to propose is to reduce the number of data essentially.
Yes,
right?
yes.
And
And reduce the radiation
There's an
damage.
even
Obviously, there are-
better way to do it, though, adaptively do it, right?
Right.
If you can evaluate the information you have currently, you can tell where to put photons.
Right.
And so it's even better, like it is sparse, but you want to go right up to the line and collect as many photons as you need, right?
So in this sense, the metrics approach that I was trying to align a little bit, right, is aligned the same. Imagine that you have a lot of data, right? Probably a large part of it is either unnecessary or affected maybe by aberrations or whatever. If you were able to say, okay, the line within my hypercube of data that grants me the best resolution for the problem, actually not even, but just the reply that I want out of my investigation, that is not necessarily the highest resolution possible. It is maybe the physical or whatever scientific question that you want to reply, right? Is this one, right? It would be sufficient to use those. Right? The problem is how to build that metric that is capable of taking the whole data, having a look and say, we can forget about, and this is the stream of data that I have somehow, right? This is the thing more or less.
Yeah, radiation damage is, we have been talking about a lot of like scientific applications of the upgraded source, but you rarely, hear any talks about systematic study of the radiation or how to avoid it. I mean, this is not only to the sample, also to the optics. But what I feel like, Xiaojing talk about, some passive or active way to avoid the radiation or reduce radiation for imaging. But I think for different techniques, coherent-based techniques, the way of avoiding image are different. And, radiation is different, and the damage, impact of damage is different. So for example, XPCS is highly sensitive to radiation damage. Sujoy probably know that, right? So because, most of the time we found out, the dynamics will change much earlier than you see the structure change because of radiation damage. So in that sense, I think it's important that, for every technique, it's very important to come out with a metrics. How do you evaluate radiation damage before you even try to, learn how to avoid it, right? For XPCS, I know a lot because we come out with many ways to try to avoid radiation damage. Recently, there was the trend of, instead of focusing beam, because all people talk about increase the flux, but now with the high coherent beam, we can afford the less flux density, but we can blow up the beam, gentle focusing or even blow up the beam so that you can make a large beam on the sample by reduce radiation damage. But that comes as a cost of your, the facility instrumentation. For example, your detector had to be far away and your wavelengths had to increase in order to, optimize the speckle size kind of thing. But what I want to say there, first, we need to come out with metrics, how to evaluate that. And we have to be smart or try to think out of the box, how to, avoid the radiation damage.
All right, thanks. So let me ask another question. It's related to what we've been discussing, maybe in terms of the data. Machine learning, how do you see the role of machine learning in the analysis of and interpretation of data from coherent X-ray, coherent techniques? Where will it be most useful? I mean, maybe in this context of adaptive data taking.
Where is it not useful? Almost anything that we do can be improved in one way or another with machine learning, but you have to be really careful, right? It's so easy to denoise too strongly, to delete signal, or worse, hallucinate signal, right? So my group does a ton of machine learning, but I showed you physics-based results, right? Because they're just a lot more reliable. So I think getting back to the beam damage question, same thing, right? You need to test and validate these things, known specimens, known reconstructions, but you really can do an experiment where you record with a huge flux and then you know the ground truth, and then you can test your machine learning network with 10% the flux, 1% the flux, 10% the number of samples, et cetera, right? Doing machine learning live too, right? Often you can get to the same answer as the physics-based methods, but faster, right? It can do, instead of 100 iterations, maybe one iteration, right? As you mentioned, it's really, it's magical when it works, right? It truly is a paradigm shift, but you have to apply it with care. It's a chisel that can shatter your data pretty easily. I just want to warn everybody about machine learning.
Yeah.
Also, Skynet is coming.
It's another problem to worry about. Any comments?
Yeah, I think I fully agree. The machine learning, in some case, can give you beautiful result, but to some extent, after it's trained, it's like a black box. Do you believe what it gives you? That's a big question. We need to be very careful with it.
I have maybe two questions indeed. One is how do we put error bars? I mean, we are scientists, right? So everything should come with an error bar. How to put an error bar on an image or a 3D reconstruction even. And second is, your question is what is not useful for, right? Machine learning. I don't know. I have the impression that it's a fantastic tool and it will help us solving all the engineering problems that we have that are obviously very relevant because as an impact they apply to physical scientific problems, and so it's important. But are they capable of making the next step? Are they creative? So if not, probably that's the thing where they are not useful to. And I hope it's the case. Otherwise, probably we'll not have a work very, very soon. So
do we want them to be creative?
No,
science?
exactly. Probably not. But I'm just asking if you see in the future, or if any of you see in the future this as an opportunity that is coming up, or effectively there is something that we still don't understand. And so the creativity will never be there, maybe. Is there any symmetry law that is forbidding this to be creative or not? So those are the two things that I would curious about.
Machine learning is fundamentally conservative. It's fundamentally better at interpolating than extrapolating, right? And this is, people run into problems when they train it and then they apply it, inference, on something that's outside of the distribution, right? That's when the creativity problem, or worse, can happen, right? So again, just careful testing, careful validation. I don't think generative AI is useful for science, but that's my own bias, right? Maybe. I really like the idea of physics in the loop, of using it to get to the answer faster, and especially for just simple tasks like denoising or knowing where to put the next flux of photons, right? These are things that are really well validated, and even if how it gets to the answer, a black box, for not knowing what's going on inside, you can test the results. It's empirically testable in the same way a lot of science is. I'm hopeful, but.
And what about the error bars connected to the quantities?
Well, so I forget, somebody was showing the 1-bit cross-validation type of measurements, right? Cross-validation is what machine learning folks use to evaluate the performance of their network. And I see it in so many scientific papers. Let me tell everybody in the room, stop doing that. Do cross-validation on the data, right? That's what you want to check. Like, you can make a measurement twice and then compare the two results, do Fourier shell correlation or Fourier ring correlation, right? You can use a known ground truth. You can do high flux, measurement, and then low flux plus machine learning and cross-validate those. So that's how I generate error bars, is by using statistical techniques against known reference data or data sets that are known to be identical. It's quite a conservative error bar. Like, it will give you a larger error bar than like root mean square or structural similarity or something, but I'm okay with a more conservative error bar.
Still, it's not clear to me how you express it in terms of a reconstructed image.
So one example would be when you say reconstruction, like, let's say you have a method, take half of your probe positions and another half your probe positions and do 2 reconstructions and then just cross-validate them against each other and then do another 50% set, another 50% set, randomly sampling it. These are very 100-year-old statistical techniques, and they generate quite robust predictions of the error, right? And you can do it in terms of any observable, whether it's phase shift per voxel or some measure of structural length. The statisticians do know how to do this. We just have to use those methods, not use the training error as our error bar.
I think I agree, and I understand it's more or less what you're saying, also because it's very logical. So.
Yeah.
But still, how do you represent together with something that you give as an image? Because the problem of our eyes, right, is we trust so much our detector that we believe that the images are correct, right? This is the assumption that we do in life, essentially. And the mirage, right, is one of the problems, right? Because your brain is tricked by the fact that it should be something that you desire in that case.
Yeah, I don't know.
How can you translate it to something that you're passing? So this is the image, and by the way, this is the error that associated.
Yeah,
that's the thing.
Well,
so
we can treat all our images as signals, right? Like as phase shifts or number of atoms or something like that. But you're right, you can't put an error bar on like, did you resolve this structure correctly, right? Or did you hallucinate with your strong denoising machine learning network? So I agree, that's like an open question.
Right, let's suppose that you can, I don't know, you can artificially blur because you are sure of certain part and less of others or whatever, right? But still it's a difficult exercise because it comes, in particular, if you start to make a multi-dimensional things, and you run out of dimension to express the problem, right? First, and this is obvious. And second is the fact that it's really difficult to convey the information. That's the problem.
Yep.
Okay. We do have a few more questions I want to go over. So I'm going to combine 2 questions into one. So your choice of the killer scientific question that you think coherence will address. So this is on the science side. What big problem could it help with? Or from the more instrumentation side, what would be a killer technological development that would, catalyze coherent scattering? So you have to choose one of those.
I have a quick reply for both.
Okay.
First, because I already wrote it in the presentation. The second one is the X-ray laser. We gained how much? ALS versus ALSU. It's a factor of 1,000 by squeezing horizontally, right? Okay. Take the whole emission of an undulator and squeeze it in energy. How many orders of magnitude do you gain? That's the changer that I think when I think about X-ray laser, okay? Good. And the other thing is, in my desire would be to try to understand where the critical exponents come from. So this is what I wrote. I thought that at a certain moment when I visualized for the first time the problem in terms of space and time, when the idea came, it was really driven by the fact that I said, oh, maybe we can understand finally, we can make a link between macroscopic and microscopic that can finally tell us something about why do we measure the critical exponent that we measure. Because it's fascinating, right? From galaxies to nanoscale of everything, we have universality class. We have no idea that I understand about, maybe it's just my ignorance, but no idea why the similarity is there.
Yeah.
So there are maybe underlying symmetries, but how this trims down the quantum to the macroscopic part and makes everything such that, for example, thermodynamically, we measure certain kind of properties is something that is still, to my belief, is completely understandable. And that's fascinating.
Others?
I mean, I don't know much about X-rays. Could you make it coherent enough to hit that 2 angstrom barrier? What would it take? People have demonstrated with electrons, ptychographic reconstructions about, 5 alpha, 15 alpha.
It's the energy. It's the dispersion relation that.
True, but you can do Bragg diffraction, right? You can do it in a statistical way. How close can CDI and ptychography get? I guess. Like, what's the ultimate limit? That's what I want. The most coherent experiment on the most coherent beamline at the most coherent source.
Let me rephrase. What is the coherent? Let's suppose that you have a perfectly coherent beam in X-rays and electrons, right? What is the energy and the wavelength that you obtain in that condition? Because for us at the moment it's 1 keV. It is something like this, right?
So is that the highest possible?
And you're walking on orders of magnitude smaller for the moment.
This
right?
is
So,
true. But
uh,
could you boost the energy then? What's the physical limit?
then the machine for the moment are the physical limit, because we are just approaching now full coherence. And as I keep saying, you always have to add the energy at which you are. And we are aiming with LSU to be full coherent at 1K.
But could you do it at 10 keV?
You lost contrast.
The problem is that you have to squeeze down so much, and also, as I said, there is the fundamental limitation, if I get the numbers correct, of the free propagation of the particles, right? I mean, you start with different sigma prime smaller than 4 pi overlap. It's exactly that the problem, right? And it's all there. I believe it's all there.
I think this question is a very big question. It depends what system you're looking at, what technique you're talking about. I can only say from the imaging technique I'm working with, I think at least there's a very rapid development in the field is apply this high resolution 3D imaging zoomable with zoomable field of view, apply to, for example, microelectronics. So microelectronics natively, it has, the chip is sizable. It can be centimeter size. In the same time, it has small features now down to maybe 10 nanometer, even smaller. So now the question is, you need to achieve such high resolution over a large field of view. That was the conflict I mentioned before. High resolution and the field of view, they don't go well together. But this laminography plus ptychography method provide this possibility. It shows it's possible to image large area to give you such small resolution to see single transistors. I think that's a very very promising area for this specific problem.
Yeah. Okay. So I'll probably skip the killer science because everyone has his own, perspective on what is a killer science. I will talk about from instrumentation point of view. So, before, with incoherent beam or partial coherent beam, in order to do coherent experiment, we have to insert a lot of optics in principle. Basically the focusing optics and beam collimation optics, right? So, but we all know that anything you put in a beam will reduce the coherence, reduce the quality. So now with a much higher coherent beam, the best optics is no optics at all, right? But that's impossible, right? We still have to put the minimum number of optics in there. So I would say we probably have to come out. I mean, I'm just saying in a fantasy world, we have to find out ways to collimate in the beam and to focus on the beam. If you have to, to deliver a high quality coherent beam to the sample, in principle, probably does have a challenge to the optics, industry or, a community. How do they fabricate, reflective optics, diffractive optics, refractive optics to make a current diffractive. Current preservative diffraction limited optics. I think that's very important for application of currents of X-rays.
Okay, so we're very short on time and I don't want to switch very shortly. There's a couple of questions that pertain to the following. So the question says, what ways can we ensure young folks can be trained to make use of the upgraded, more coherent X-ray sources going forward? There's another question down here that pertains to implementing, and hereby, as of this point, my postdoc Rurev suggested to implement a journal club style or recurring seminar on Zoom, kind of like what Jerry Seidler did for, I don't know if you all know what he did during COVID that he keeps doing now. Something like a recurring Zoom seminar. But anyway, to the panel, how do we get young people involved?
My opinion, and from our experience, for each beamline, for example, they always have some techniques more mature than others, and some techniques we are still developing. And then our attempt is trying to develop some, for example, re-interface for those mature techniques, and then with very minimal training, the users know how to use it. But on the other hand, for those under development tools, I don't think it's not supposed to be so easy to use anyway. So once we are confirmed and make sure this technique is working reliably, then we try to make a easy user-friendly interface and deliver to users.
You gave us a nice.
Yeah.
My answer is much more radical. Radical open science. I don't agree with what you said. So it's nice to have a great interface to dumb it down, right? It does lower the barrier here, but we can publish every data set recorded online. We can publish every code used to process it. We can expand it a little bit and explain why you're running these different steps. And you can do something similar in the experiment, right? You can record a video, you can sort of explain the steps. If you publish all the sort of research analysis methods online, right? Students can teach themselves, and especially if they can come back to you with questions, with feedback, right? You can make a virtual beamline essentially in code on the web now in a couple days. Like the barrier to entry is very low. And you could show real experimental data, real experiments with artifacts and say, this is how you shouldn't do it, this is how you should do it. Now the problem is person power, right? It does take some time, so give up sleep and just do it.
And also it looks like not all the users they care about how you get the image. For example, maybe they're focusing on the scientific problem there. What they're asking for us is like the images, and then they do the follow-on data analysis. Yeah, but those users, I think, have this easy.
But then that data analysis should be published too then, right? Like the high-level scientific analysis should also be explained and published. The example data sets is the thing I keep coming back to, right? That's the best thing we ever did for teaching. We publish everything, good, bad, and ugly now. And my God, it helps because you can point to it and say, don't align the microscope like this.
Yeah, that's good. Okay, yeah, Sujoy.
I was thinking that we need more places to do this experiment because all the beamlines are super subscribed.
Yeah.
Which tells me that there are more people who we can accommodate and thereby increasing the number. I mean, the number will only increase when there are more people to do experiment. There's a reason that many people are doing crystallography because there are that many diffractometers around. There was only 2 diffractometers like CSX and cosmic half running. There are only that many experiments that can be done.
I was about to say exactly an equivalent thing, which is I think that the problem is that you have to spend time aside the data. Now, I understand that people don't want to use to have the data. They want to have the high level quality images or whatever in the case of reconstruction. But this is actually the way to generate monsters. It's exactly what you were saying before in saying, you know, that you have to understand what you're training things on and what the boundaries are. Otherwise, you may generate or hallucinate the data you use this expression, which is very powerful. And I think it's exactly the same thing. We need to be sure of being the ones that somehow are driven to errors because we learn instead of having something artificial that does it for us, and then we trust them. There is at least a kind of balance, right? So the problem is that if you publish everything, it's needed an infinite amount of time and energies to go through. And so the learning process typically is it has been organized over years. I mean, we talk about history here, right? And people that are bringing their experience to the other people that are younger, so they have more energies, but you somehow guide them, and you may show some selected errors or whatever, as you were saying, and finally this guides the evolution of the human brain in the right way because it brought us up to here. Going out of this very traditional way, I don't know. I'm unsure it will. Maybe you're right, but it's a little scary somehow. Obviously, having a lot of support is fantastic. Don't get me wrong, but still, it's needed probably. Interaction and spending time, dedication, I would say.
No substitute.
And certainly having instruments is fundamental because if we don't have real places where to play, we're not there.
Okay, so we are at the time in which we're supposed to take a photo.
Yeah.
But at this point, I'd like to thank the panel/speakers for all their organizers for organizing. Sophie, hope you're feeling good.
For all of you.
And to all of you for coming and participating.
right outside the front entrance of the.
Photo, so now it's photo. Is that what it was?
And then we go back to the tent for the
Then we,
reception.
after the photo, we go back to.
Just shoot me an email. Always happy to. Yeah, I'm also interested in your stuff. too.
Here, apparently.
Yeah, maybe I have some backpack. And I know they like to not see badges on these pictures, so if you're talking or something,